In this tutorial, I'm going to show you how to use the DTOcean WEC simulator tool to generate array interaction matrices for use in the DTOcean Hydrodynamics module. To do this, I will first open my DTOcean installation by hitting the Windows key and searching for DTOcean, and then hitting Enter. The DTOcean 2 splash screen now appears. Once the DTOcean 2 installation opens, I will then open the example project that can be obtained from the DTOcean GitHub. This can be seen by searching for DTOcean GitHub. And then under releases, you can see under version 2 that there's the when executable that should have been installed, and then there are the getting started files. Inside the getting started files, which are shown here in my downloads, is the zip file, and when you unzip this file, you get the RM3 10example.dto file, as well as a folder called reference model 3 model data, inside of which is a WEC solution.h5, which I'm going to be showing you how to generate today. But what I'm doing right now is loading this RM3 10example.dto file. To open it, I'm going to click File, Open inside DTOcean, then click on RM3 10example.dto, then click Open. Once this opens, we can see in the pipeline, under Modules, Hydrodynamic, there are a number of green circles indicating that these fields already have data and are ready to be run. There is one blue diamond, which is an optional data field, and then a red square indicating that you must put data in here. We could load the .h5 file that I showed you inside the RM3 data, but today I'm going to show you how to generate that file using, at the top, Tools, and then clicking WEC Simulator. Once I click WEC Simulator, a new window will open. At the top it says WEC Analysis. Inside here I want to start a new project, so I click New Project. Once I click New Project, I need to specify a folder where I can read and write output. So I'm going to navigate to a folder, which I call DTOcean WECSim. I'm going to delete the folder that's already here. And I'm going to create a new folder called Output, and then click Select Folder. If I were to select a folder which already exists, for example, the output already exists but is empty, and then click Select Folder, a pop-up window will appear which will let me know that this project folder is not empty. I need to select another folder or clear the actual folder. If you click Clear, you can use this folder, but it will delete all the data in that folder, so be careful if you use this option to clear. Now that I have specified my output folder, I want to run Nemo. Once I click Run Nemo, the WEC Analysis will open into this screen shown here with 3 smaller windows, which I can show you all of by at the top clicking Windows and then clicking on Cascade. Once I click Cascade, all the 3 of the windows shown here have cascaded to the top left corner, and I can show the data visualization by clicking on this top right corner. I'll pull it forward, then I'm going to click on Hydrodynamics again, and you can now see that I have the Hydrodynamic data visualization and performance fit modules also listed here. We have to start by listing our hydrodynamic setup, which begins with the total number of independent degrees of freedom. In order to see what this is, we want to take a look at what the device looks at, which we can see by looking at a totally separate code, which happens to have run a reference model 3 tutorial. And this code is called WECSIM. I search for WECSIM, and I'm going to go to the WECSIM github.io, the documentation page. And then I'm going to click on tutorials. Once I click on tutorials, the first tutorial is a two-body point absorber, or RM3. And the device geometry is shown here. There is a silver spar or heave plate, and it has a circle at the bottom and a shaft that extends upward. And then a yellow float is the second body. And the surface water level is shown about midway through the float. So that's the geometry we're working with. And so one more thing, in order to understand the total number of independent degrees of freedom, I am going to open a picture. So here is a picture that I have taken, and I'm going to use for this discussion. What this shows is two rigid bodies connected by two what they call revolute joints, which only have 1 degree of freedom. So I'm going to rename those, and they're connected to the ground. So in our case, I'm going to edit this picture. And so again, we do not have a revolute joint. So this is now going to be what I'm going to call 6-DOF. So 6 degrees of freedom. So each one of these C's is a 6-DOF joint. And then instead of the ground clamp, we're going to have a surface water clamp. So this will be, I'll just call this surface water, SW. So this is our surface water. So we can see that between the surface water and our first body is a possible 6 degree of freedom joint. And then again, between the first body and the second body is a possible total number 6 degree of freedom joint. Let's go ahead and save this. And so what we need is the total number of independent degrees of freedom as specified here. So the way that this would work to orient it correctly, we'd have to rotate this 180. So it'd look like this, right? The surface water is here. Our first body is this, is the spar, and then the second body is the float. I'm going to rotate this back around. So between the surface water and the first body is 6 degrees of freedom. And so we're going to have a total number of 6 there, and then in between, so this is 6, in between the spar and the float can only move in the heave direction with respect to the spar. So the C2 is going to be 1 degree of freedom. So the total number is 6 plus 1, or 7. So we're going to put 7 total number of independent degrees of freedom. The next data field we need to input is the ID of the independent degree of freedom connected to the PTO, which is our float, and it's the 7th degree of freedom. The ID of the independent degrees of freedom connected to the mooring. So this device is going to be moored in the surge, sway, and yaw direction, or our 1, 2, and 6. So 1, 2, and 6. The number of frequencies to analyze and the min and the max I'm going to get by looking at the WECSIM page. So WECSIM, again, totally separate code. On their actual code hub, we can navigate to their tutorials, look at their reference model 3, tutorials Bimeo, Nemo, reference model 3. inside here, there's a nemo.cal file. And we can see by looking at what they ran a total of 260 bins between 0.02 and 5.2 radians per second. So that's what we're going to put in here. We're going to do 260, 0.02 and 5.2. Number of angles to wave analyze. This must be at least 8, but here I'm going to do 10. The water depth is going to depend on our site. And in this case, in our lease area at Humboldt County, California, the bathymetry ranges from 40 meters to 90 meters. So I'm just going to put in the average of 70. We cannot put in 0 meters for an infinite water depth if we want to generate the array interaction matrices, which we do need when we're calculating the power in the hydrodynamics module inside the larger DTOcean simulation. Not to be confused with the hydrodynamics module here, which is specified for a NEMO boundary element method or BEM solution. So this can be as low as 20 and 20, but I'm going to run 50 and 50. Next, we need to put in the point of applications of the equations of motion expressed in the global coordinate system mesh file. So I'll show you this in the mesh file, but for here, just know that it's 0, 0, 0. Our total body can move in all 6 degrees of freedom. And then looking at the single body specification, we're going to start with the spar. So I'm going to browse for a mesh file. What I did to generate this mesh file was I took the mesh file which was run inside WECSIM, and that case was run axisymmetric, meaning that only half of the device was run and it was only run at one angle, and then you can just move that around because it should be the same from every side because the device is axisymmetric. So since they only ran half the case, I opened the mesh file they created in Rhino. I then mirrored it and then re-output it so that I could run multiple angles because the hydrodynamics module here does not consider the axis symmetry of the device. So we have to analyze more than one angle. Okay, so this is in my clone of the WECSIM in tutorials, Vimeo, Nemo, RM3 mesh, and I'm going to start with spar2.gdf, and I can now view that mesh. Here is the 000 point application that I told you we'd be able to see in the mesh file. It's specified in the center of the cylinder, and you can see that it's a fairly fine mesh file for our spar. And again, this is defined at the surface water level, not at the top, as we can see from the tutorials page. It's cut off here, and this will be more obvious when we look at the float. So I'm going to go ahead and close this. I do want to quit this mesh viewer. Next, we need to specify an ID, which can be anything, and I'm going to specify it as 0. The center of gravity with respect to the body coordinate system, I'm going to get from the WECSIM page is negative 21.29. This allows us to adjust our coordinate system, but we do not want to do this, so we're going to input all zeros. The relative degrees of freedom between the body and the parent, as this is the parent, we're going to leave this alone. Now here we're going to specify our children, and this is where we're first going to specify our child ID. I'm going to specify the child ID as 1, can be anything. And then the coordinate system position is going to be 0, 0, 0. So it's going to be defined about this same surface water level at the same location as the cylinder connected to the spar. The parent body ID is going to be -1 because this is the parent. The body mass in kilograms we can copy from this page, and it'll be 878, 300. And the body of a moment of inertia tensor we can copy from here, separating our columns with commas and rows with semicolons. So this will be 94, 419615, comma 0, comma 0, semicolon 0, comma 94407091, comma 0, semicolon 0, comma 0, comma 285422225. And then once we're done with this body, we're going to click add body description. Excuse me, I messed up when I did the center of gravity. This should be 0, comma 0, comma negative 21.29 in the z direction. Now I leave this body description alone and I only adjust the single body specification, this time looking at my float. So I'm going to browse my mesh file, open my float file. I can now view the mesh, and as I said, this is defined at the surface water level, and the 0, 0, 0 coordinate system is at the center. This mesh looks good. I'm going to exit. Yes. Some functionality that is missing from Nemo but is available in WEMIT is the ability to treat these planes which are connected to each other on the inside of the device as dipoles, and that can be read about in the WEMIT manual, but should just be noted here as a possible source of error when running these types of devices. So now moving on with my float, the ID I've already defined previously to be 1, so I have to keep that the same. The center of gravity is going to be negative 0.72. We're not going to adjust the coordinate system, and here we do have a relative degree of freedom between the body and the parent in its heave, right? So the first input that we need to do is the degree of freedom type, and this refers to a Nemo convention where 1 is translation and 2 is rotation. So we do have translation. And then AX, AY, AZ refer to unit axes. So the unit axes that we translate about is the Z direction. So this will be 1, 0, 0, 1. The child has no child, so this is blank. The parent body ID is 0. The body mass in kilogram we can get from this page, and it'll be 727,010 kilograms. And then again, we will separate our columns of our moment of inertia tensor with commas and the rows with semicolons. So this will be 20,907,301, 0, 0, semicolon, 0, 21,306,091, 0, semicolon, 0, 0, 37,085,481. Let's add that body description, and now we can check our inputs. I'm going to expand this window and then expand the Hydrodynamics module window inside the WEC Analysis tool. I'm going to double click on the column, the inertia column, to spread it out. There we go. So again, this for the spar, we defined our parent body to be 0. It has a larger mass and a larger moment of inertia tensor, which seems to have the same form as the one below, as we would expect. Center of gravity is negative 21 in the Z direction. That seems correct. We're not messing with the orientation of the coordinate system. Degrees of freedom with the parent. This is the parent, so it should be blank. And then we specify the child ID. It's 1 with the same global coordinate system position, 0, 0, 0, and this is negative 1 for the parent body. The mass of the float should be a little bit less, and the moment of inertia tensor should be a smaller number than above and have the same form. Center of gravity looks correct, and the parent body D is 0. All of this looks correct to me, so I'm ready to submit my inputs and then click calculate. At this point, this window freezes and the interrupt key will not work. And this sort of wheel comes up anytime you're in this, hovering over this page. I want to mention that the current run, as I have set it up, takes about 3 days to complete. If you want a simulation to complete quicker, reduce the number of frequency bins that are being analyzed down to 100 or less. Before I wrap this up, I want to show you what we have created by going to the output folder. We can see we now have these files which we have created. Inside the hydrodynamic, we can look at our nemo.cal, which if you remember when I grabbed my frequencies from the separate WECsim code, I opened the nemo.cal. If you're familiar with the nemo.cal, the only difference is really this is the modification made to the NEMO code, where there's some calculation for the array interaction matrices, which you can see we didn't input this number, but we told it to calculate 50 and 50 for our interaction matrices. So with that, I'm going to go ahead and wrap up this tutorial. In the next tutorial, I will show you some data visualization from the output of NEMO, then how to fit the experimental data to your NEMO data, and then lastly, how to generate that H5 file to use back here in our larger DTOcean program.